In fluid mechanics, density is important to us because we will soon need it to quantify mass flow. It's a straightforward concept to begin with, but we find that once we open the door, there's more to discover than we bargained for. It's not that complicated. Let's take a look at it together. We write density with the Greek letter rho. It's very easy to quantify. Essentially, you take the mass, m, you divide by the volume, v, and you get an amount in kilograms per meter cube that tells you just how much mass per unit volume there is where you're looking. Be careful with the notation here. The letter rho is easily confused with the letter p. Rho for density, p for pressure, very different concepts. Same thing for v, curly v for volume here, v for volume, v for velocity, also very different concepts. Not every fluid dynamicist will confess to it, but pretty much every one of them, in the moment of weakness, has mixed up some of those symbols as a student. So be very careful as you write them down. Here are a few example values of density. Air, at ambient conditions here in the room, has density about 1.2 kilograms per meter cube. Hydrogen on the left, much less, but both of those values will be stuck up on the left of the axis over there. If together on the same axis you add water, liquid water, 1,000 kilograms per meter cube. You can change the density of water a little bit. If you add salt, it increases. If you heat it up, it decreases. But in general, 1,000 kilograms per meter cube is a good starting point. Variations around this are just a few percent. In red here on the diagram, around water I have added a few values. Oils are a bit less dense at about 850, 900 kilograms per meter cube. And blood is a bit more dense than water. Blood is essentially made of water with added solids. And completely on the right of the axis, I have added honey at 1,000 kilograms per meter cube, approximately. In all of those, you should keep two values in mind. And these are for air, 1.2 kilograms per meter cube at ambient conditions, and liquid water, 1,000 kilograms per meter cube. Density is important to us for two reasons. One is that it drives buoyancy. Buoyancy is this flotation force that is going to drive the movement of, say, a bubble of air that's rising inside water, or cold air that's sinking inside warmer air. But the main reason why we study it now is that it appears in the equation for mass flow. Mass flow determines how much mass is coming in or out of something of interest to us, so it's very important in engineering. Now, if you have done some thermodynamics before, you may have encountered density already. And you may remember it depends on pressure P and temperature T. Well, it's pretty straightforward to understand, right? If you take a gas and you push on it with pressure, you tend to squeeze it to increase the density. Same way, if you subtract heat from it, you tend to cool it down and its density will again increase. If this is a bit blurry to you, do spend some time playing with the simulation PhET from the University of Colorado on perfect gas. And you can heat up and cool down and squeeze and expand the gas and see how the molecules all play together. In thermodynamics, we call this the state of the fluid. Essentially, if your fluid can be modeled as an ideal gas, and this is a good case, then you can quantify density very easily, right? You take the pressure, you divide by the temperature and the constant R that depends on the nature of the gas, and voila, you've got the density. In the cases where your fluid starts to condensate or to change phase in general, yes, starts to boil, starts to condensate, then there's no longer an easy equation you can use and you will need to look it up, typically in tables of pre-measured values. If you're a bit rusted with this and you need a refresher, there's a very good thermodynamics book you can download entirely for free without registration on thermodynamicsbook.com. Be aware though, I'm very biased when I make this recommendation because I'm the guy who wrote it, so take my advice with a grain of salt. So here now we are entering an ocean of variables. Check it out. Density is connected to pressure and temperature. So far so good. This is ordinary thermodynamics. Pressure is connected to velocity. Now, we'll go into detail into the relationship between pressure and velocity. But for now, it's enough if you just imagine that a particle of fluid, when it goes towards an area of high pressure, will tend to decelerate. And when it tends towards an area of low pressure, it tends to accelerate. Yes. So there's a connection between pressure and velocity. But wait, velocity is where the fluid is going, right? So where the fluid is going will end up determining, at least in part, whether it's heated up or contracted or compressed or expanded. So certainly whether the density and the temperature will change. So you see what's happening here? We are entering an infinite loop. We started with a perfectly legitimate and pretty simple question, which is right here in space. And this point, what is the density? How much mass per unit volume do I find? And we find out that in order to answer this question here, we need to calculate the entire flow and know where the fluid is going everywhere, all the time. Oh, the sun is rising. What a sight. At the top, the movement of the air is wind, is driven by pressure. At the bottom, the trees are heated up by the sun. They release heat into the air and release water into it. The air is heated up, accepts the water, expands, and as it expands, it starts to rise. As it rises, it cools down, it starts to contract, and then it starts releasing some of the water, and some of that water becomes visible as condensation to our eyes. And then it cools back down, sinks back down to the bottom, and the cycle repeats. First thing you might be thinking when you see such a flow is, what an amazing planet to be living on. And of course, you may feel some anxiety or dread, because how on earth are we going to calculate this flow? The bad news is, there is not one equation that you can solve that will allow you to describe this entire flow. It's a complicated flow. There are many processes here that depend on one on the other. And you have to believe me when I tell you that experienced fluid dynamicists have learned to listen to a little voice at the back of their head. And this little voice tells them, okay, relax. Yes, it's very complicated. Yes, everything depends on everything else. But what are you trying to achieve exactly here? Try to focus on that. And in the meantime, take this enormous, intricate problem and try to break it down into a set of smaller problems that you're going to be able to solve one by one. So what we're going to do now with density changes is we're going to neglect them. And yes, you're allowed, and in fact, explicitly encouraged, to neglect density changes in 3 cases. The first case is liquids. Liquids have a very high bulk modulus, which is a way to say they're very stiff, very high to compress. So unless you're really talking about specific cases, most of the time liquids have constant density. Second condition is gases, but in a few conditions. Now we're going to read this condition slowly. It's a lot to unpack. Gases flowing freely without heat transfer at moderate speeds. Flowing freely means the gas is not constrained and put in a box, like for example, say a cylinder with a piston compressing it. It's always free to escape and move around or inside the object. Without heat transfer is because adding heat to a gas provides it with lots of energy with which typically it will do work, means expand, and have its density change. And the last condition is at moderate speeds. Typically we're talking about hundreds of kilometers per hour or miles per hour or less. And the third condition in which you're allowed to neglect density changes is all the time in your first approach. This is because we need to break this dependency of the variables. We need to find a way into the calculations so we can start analyzing the flow and solving for the dynamics. I have put myself in an uncomfortable position here because I'm telling you to neglect density changes, but I'm not really giving you the tools that you need to verify whether this makes sense at all, right? So on my to-do list for the coming videos are 2 things. The first thing is we will need to explore what exactly causes the density to change in a fluid flow. And the second thing is that we need to make sure we really understand what the influence of density changes is on the dynamics of the flow itself. To sum up then, we're going to deal with density like the professionals. And this means, first thing we're going to do is to assume it is constant and uniform, which means we take one value of density here and we assume this to be the same value everywhere all the time. Then we proceed with the analysis, which means we calculate the flow by hand or with the computer code. And then we'll check and adapt if necessary. I know this is very difficult to hear, especially if you like to go to the bottom of things, into the physics of the flow. But fluid mechanics is not just physics, it's an engineering discipline. And we need to break this dependency of variables. We can't afford to wait to be finished with the entire calculation in order to begin, right? And this puts two things on our to-do list. One is that we will need to study the exact influence of density changes on the dynamics of the flow. And the second thing is we'll need to learn how to predict and to check whether our assumptions were correct or not. In all of this, get started. As you begin any calculation, look up the one value of density for the flow that you're going to use. 1.2 kilograms per meter cube for the air at ambient conditions, 1,000 kilograms per meter cube for water. Get started, and I'll catch up with you. I'll see you in the next videos. Hi, I am Olivier Klein, and I'm recording a video course in fluid mechanics. If you find this video useful, check out the rest of them at learnfluidmechanics.com. I hope to see you there. Take care.